Hello, and welcome to another one of Ethan's engineering videos. I'm Scarface Ethan, and today we're going to be talking about Broyden's method, and specifically how we can use that to solve for an improved Jacobian iteratively. So up on the board right now, I have Broyden's method, which is, as you can see here, it tells us that a new and improved Jacobian Jn can be manufactured using an old Jacobian Jn-1. This n-1 tells us it's slightly less optimized and less accurate. And we're adding to it this big term right here, which is the change in the final values minus the original less optimized Jacobian multiplied by the change in our independent variables, our delta x, divided by our delta x squared multiplied by the transpose of our delta x. So we're going to solve this using our own statements of truth, because again, we're trying to solve for the roots of a function. That's why we're iteratively solving for matrices that represent our Jacobian, because that way we can solve the root of a function with minimal computer resources. And iteratively refining a Jacobian is probably the most efficient way to do that without doing some really, really complex math that I don't want to learn or am not educated about. So the reason I have Broyden's method written up on the board to start is so that when we find it with our own notation and it doesn't look quite the same, I can algebraically prove that they are the same using his notation, and then we'll show that what I have is still accurate and good. So let's get started. So as I said before, we're starting to solve the root of a function that we don't know the root of, and we also don't know the true Jacobian of. So in order to do this, we're going to have to start with an approximation, which is going to be the linear approximation of a function, which just tells us that f of x is equal to f of, I'm going to call this, this is our known point, so it's going to be f of xk for known, plus the Jacobian at that known point, multiplied by the change between x and our known point right there. So this is our linear approximation. I'm going to make this a squiggly line, so it says approximately. So it says that when we move from our known point to some new point, if we know the Jacobian, the difference between those two inputs multiplied by that Jacobian will give us, of course, that added to our original point will give us our new point. So theoretically, if our line is linear and we know our perfect Jacobian, this is fairly accurate. So since we're looking for the root, obviously the point we're looking for is going to be 0, and we want that to be equal to this side of the equation. So we're starting again from our known point, f of x known, and we're going to add to it our Jacobian times the change in our points. However, we don't actually know our true Jacobian. That's the whole point of using this iterative refinement, is that computing this straight out can be fairly expensive for large and complicated functions. So instead, we're going to approximate it, APPROX, and I'm going to use D because D stands for discount. So we're going to call this dk, so it's a discount Jacobian at point k between the points x, k plus 1, and x, k. So this is the next point over from our known point, k plus 1. And so what we're going to do is we're going to solve for this dk. So knowing that we want our Jacobian to take us from our known point to 0, we're going to solve for the Jacobian the approximate Jacobian that does in fact take us to 0. So theoretically, right, we subtract this over, we divide by the difference in our x's, and we've got our Jacobian. Boom, we're done, right? So we plug that in, and it should spit out 0, right? But unfortunately, if it were that easy, we wouldn't have Broyden's method, and math would probably be something everyone could major in. Unfortunately, this right here is probably not going to equal 0. This right here is probably going to equal some f of x k plus 1, which is not going to be equal to 0. And y is what we spit out when we do this, right? When we do this, we check it against our actual formula. We plug in this x number with our Jacobian, and we see that it's not actually 0. So what gives? Well, that's because our Jacobian isn't our actual Jacobian. It's because j of k is not equal to d of k. So how can we go about fixing this? Like why we know why it doesn't work now, but how can we improve d of k to make it more accurate? Well, now that we know the output from moving from our known point to our next point, we can actually use this to back solve for a new Jacobian, like we did right here. So what we're going to do is we are going to now set this f of xk plus 1 equal to f of xk plus some new Jacobian. Let's see here. We're going to call it d of k plus 1 multiplied by k x of k plus 1 minus x of k. And so now we can solve for this Jacobian. And I do realize I did make a mistake right here. We're not actually solving for our d of k. This is something that we're kind of just making up. This is our first time since we're starting here, we're going to be making this up. So this is going to just be something we invent. And we're going to be actually solving for our xk plus 1. And then we're going to take the function at xk plus 1. I realized I misspoke there for a second. We're not actually solving for the approximate Jacobian yet. This is something we just made up. So I'm going to write make approximation. So we're just going to make up some approximate value of our Jacobian at this point, and then figure out at what new x value that Jacobian tells us should take us to 0. And when we solve for that x value, we're going to find that it's not actually equal to 0. And that's because our approximate Jacobian is not close enough to our real Jacobian. So what we're going to do now is using this new information of, well, this point at x doesn't actually take us to 0, it takes us to 3.5. We can now take that 3.5 and back solve, based off what we had before, for a new Jacobian that accurately predicts going from xk to xk plus 1 takes us to 3.5, not 0. So now we solve for this, and we have an improved Jacobian. So that's essentially what we're doing, and that's the peasant way of doing it by hand. We do this over and over and over, and eventually we'll get to something that's actually at 0. However, Broyden's whole point was that he didn't want to do this a bajillion times because that wastes a lot of computer resources. And the whole reason we're even bothering to iteratively improve our Jacobian is to save on bits and bytes. So what Broyden does instead is he looks at the relationship between d and x and dx plus 1. So what we're going to do now is we're going to actually subtract these two functions because these are both true. Obviously, they're true, and it'll tell us about the relationship between the two of them. So I'm just going to put a little negative sign and a line over here. And we're just going to subtract this bottom one, or I guess this one would technically be, this one's going to be positive and this one's going to be negative. So we're going to subtract this top one, the older one, from our bottom one and see what we get. So right here, we have our new output point, f of at xk plus 1 minus 0. So that's just going to be f of xk plus 1. And we're going to have an equal sign there. And right here we have f of xk and f of xk, so those cancel out to be 0. And then plus, well, here we have dk plus 1 minus dk, and both of those are multiplied by xk plus 1 minus xk. So we're going to pull that out from our subtraction. So we're going to have parentheses d of k plus 1 minus d of k multiplied by x of k plus 1 minus x of k. So this right here is the first relationship that Broyden really pioneered and looked at and said, look, the difference between our Jacobians, our old approximation and our new approximation, multiplied by the difference between our known point and our first searched for unknown point, should be equal, I'm just going to ignore that 0 there, should be equal to the actual value of our function at that final point, which is pretty novel. But it makes sense since we were aiming for 0 and we landed somewhere else. The difference between the difference between our navigation system that said we're going to 0 and the navigation system that accurately said we were going to 3.5, that difference obviously should be the difference between 3.5 and 0, since the actual value is the difference between 0. If we were looking for whatever takes us to 3, it would be the difference between what we actually got and 3. So it tells us the variation. But because we were looking for 0, this is just a single number instead of a difference, and so we can actually use that in an interesting way. And that's why we're going to scoot over a little bit and move on to our next thought. That since, improving our Jacobian required moving along some direction between xk and xk1. So I'm going to rewrite that over here in a new format just to make us more familiar. So we have right here that f of xk k plus 1 is equal to, now the difference between our two approximate Jacobians, I'm just going to call delta d, and the difference between our two x values, I'm going to call delta x. So again, this tells us that the difference between where we expected to go and where we actually ended up, based on our Jacobian multiplied by the amount we moved, gave us the discrepancy between the root we were hoping for and the value we actually got. So Broyden then asked, well, what happens if we were instead to redo this, but move in a totally different direction? If we were to move in some y direction, so if we moved in y, which is perpendicular to x. So what does it mean to be perpendicular to x? Let me say y, comma, where y and the cross product, actually we're going to call it delta y. If we moved in the delta y direction instead of the delta x direction, and where delta y multiplied, dot multiplied by delta x equals 0, so it's perpendicular. What it means for something to be perpendicular, of course, means it shares no components. Since this can be a multi-sized matrix, delta y and delta x don't just have to be a single number. They can be an array of 8, 10, 20, however many you want. But to move in some delta y where the cross product with delta x is 0 means that none of those components are shared. And what that means is if we were to start all over again and move in this other direction, our improvement along the delta x direction won't actually help us at all. It won't actually have improved our Jacobian when we move in the delta y direction, because obviously the only information we got was from moving in that delta x direction. Moving in that delta y direction from that original starting point, we won't know anything. That information isn't applicable. So what that tells us is that moving in the y direction from either our original starting point or our improved starting point, or our improved Jacobian. Let me rephrase that. Let me take a second, not trip over my words. There's something beeping again, and it's really annoying, and it messes my train of thought up. If we were to move in the delta y direction, because our original approximate Jacobian and our new improved approximate Jacobian both differ only in the delta x direction, they will give us the same output point, whether or not we use d of k or dk plus 1. So essentially what we've said is this error will be the same whether or not we use our improved Jacobian. So d of k times delta y will be equal to d of k plus 1 times delta y. Again, the only difference between these is an improvement in the delta x direction, and since we're moving in a direction that is perpendicular to delta x, that improvement will have no effect on the error when we move in the delta y direction, the error from 0. Now, the other thing Broyden said was, because this is true for this new direction, stop beeping please, because this is true for this new direction, we can actually say something very interesting about dk and dk plus 1 and delta y. And namely, that is, if this is true and dy and the delta y and delta x do have a cross product of 0 and they are perpendicular, we know that, I want to make sure I'm picking the right d here. We know that, here we go. We know that delta d times delta y will be equal to 0. So if this is true, right, then we know that the difference in d in the y direction is non-existent, because the only difference, as we said before, is that delta x. There is no difference between delta y. However, and I'm just going to say if, I'll put an arrow there. Again, that's if delta y and delta x, the cross product is 0, or the not cross product, the dot product is 0. They are perpendicular. However, delta d times delta y has to be equal to f of x k plus 1 if that's a bad delta y is equal to delta x. So if our delta y, our new different direction, is actually just delta x again, we should get the exact same output, which again is common sense. If we do the same thing twice in math, we should get the same result. But because both of these need to be true simultaneously, what Broyden really pioneered was he looked at this and said, how can we describe this relationship between the difference in our Jacobians in a succinct, easy way? And he came up with this function, which I'm just going to call g of y, g of delta y, which essentially makes both of these true while also following everything that's led up to this point. And it's so simple, it might make you a little upset. It says that delta y cross dot product with delta x divided by delta x times delta x. All of this that whole fraction multiplied by f of x k plus 1. That's his function. So what is this output? Well, if we plug in the cross product of delta y and delta x is equal to 0, so that's some whatever delta y that is, well, when we do that up here, obviously we get 0, and this whole function becomes worth 0. So g, that's a horrific g, I apologize. So for g of delta y is equal to, or I'll just say, yeah, for g delta y is equal to, or not equal to, but I'll just say for g of delta y. For the delta y where this is true, we're going to get 0. However, if we use g of delta x, you notice that this delta x dot multiplied by delta x is divided by the exact same thing on the bottom, so we're going to get 1 in this fraction. That multiplied by f of x k plus 1 is going to give us f of x k plus 1. So you see, this g of y does in fact match both of those statements we made earlier about moving in a new perpendicular direction with information not being conserved because it's not applicable anymore. So how does this g of y help us at all? Well, this is kind of the foundation for Broyden's big method up here, and we're going to convert that from here into that. Of course, we're going to stop intermediary into my own, like how I think is most comfortably descriptive, but then we're going to prove that again it does match Broyden's. So we take gy, which we're not, we don't need to say what it spits out anymore. We can just look at the expression itself, and we can say delta y times delta x, and that, and that. Okay, so I don't know if I really want to bother rewriting it again just to immediately change it. But the first thing we want to do is we're going to want to look at what delta y actually is. So again, since delta y and delta x can both be as many independent variables as we want, we know that both delta x is going to be some matrix up here, and that's going to be a 1 by n, and delta y, even though it's in a new direction, is still going to be approximately the same, is going to be the exact same size because all we're doing is moving in a different direction. So these are both going to be n by 1 matrices, and so this is an n by 1 dot multiplied by an n by 1, which gives us an n by n matrix on top. And that's kind of dumb and makes our equation just very complicated to work with. So what we're going to do is we're simply going to flip these around. We're going to swap this order, and we're going to transpose this delta x. And the reason we're doing that is because if we were to do delta x transpose, it would be a row instead of a column. So we would have a 1 by n, and when we multiply those together, we could, instead of having to do a dot product, we could just do regular matrix multiplication. So we're going to rewrite this, implementing that change, because it will still give us the exact same effect as long as we both transpose x and t when we flip them around. So we're going to rewrite this as delta x transpose times delta y over delta x dot multiplied by delta x times f of x k plus 1 in parentheses. So all this has done is made it a 1 by n times an n by 1 matrix, so it would be a 1 by 1 matrix, and we can just do, oh, what's the word I'm looking for? We can just do a matrix multiplication instead of a dot product. But then what we're going to want to do is we're going to want to look at this, and we're going to want to switch, just because matrix multiplication will be a little bit nicer and cleaner that way, we're just going to switch delta y and f of x k plus 1. We're going to move this one all the way over to the left side. So we're going to do the exact same thing, but instead of getting a 1 by 1 matrix, we're going to get an n by n matrix. Because again, this is a 1 by n, this is an n by 1, and so we're going to still keep the same outcome that we got when we used delta y dot multiplied by delta x, because again, we need a matrix on top of this function. Because right now, this is a 1 by n, and this is an n by 1, and so they would make a 1 by 1 output. So we want an actual n by n matrix on the top of this division. So we're just going to move this guy over here, and we're going to scoot this one over. So we're going to rewrite this as f of x k plus 1 times delta x transpose over delta x multiplied by delta x, and then not equals, and then we're going to have our delta y over here. So again, this is what we have right here. But now that we've kind of rewritten this in a way that's actually more legible and usable, what do we do with it? Because this isn't exactly enough. Until you remember that this right here is supposed to describe the output, right? The output of the difference in our Jacobians. So we can bring that back in because, again, what this tells us is the g of y tells us the output of our Jacobians, what the difference between our Jacobians when multiplied by some change in initial starting point or independent variables is. This is going to be equal to our delta d. So what exactly is our delta d? Well, again, remember we defined that as just the difference between our two Jacobians. So we can rewrite this as, since again this is dk plus 1 minus dk, we can just move dk over to this side. So we have d of k plus 1 is equal to d of k plus f of x k plus 1 times delta x of t over delta x. And at this point, I'm just going to put this in here and say it's squared times delta y. And this right here, this is Broyden's method, right here. And you might be looking at it and saying, wait, hold on, that doesn't exactly match. Look, all you have up here is multiplication, and over here, you've got a whole bunch of other garbage. I forgot to actually cancel out that delta y really quick. That's my apologies. This right here, I just realized what I was catching up. As I said, this is equal to delta d times the direction we're moving in. So this would be delta d times delta y. But again, you notice that Broyden's method, once we've actually taken care of our delta y's, you see that they just cancel out, so we can just cancel that out. I realized I was looking at it, I was like, why is there a delta y in here? There should be no delta y in Broyden's method, and that's because the delta y was just for the sake of defining the relationship between the two. I just raised my eyebrow, and I think it pulled on my stitches a little bit, but that's fine. What we're saying is that the difference in our delta d times our delta y is equal to this relationship that we just described down here with our g of y function. Because again, g of y represents the outcome right here, either 0 or f of x, and that's this thing right here. So this is our outcome. So that's what is equal to our g of y function. Let's put a little arrow there to signify that they are the same, just to make sure I and you don't get confused. Because I said the output of this doesn't matter, like we weren't using it, but we were, because again, that's what we set equal. Because again, g of y is just a substitute for our dy, delta d, delta y. So again, now that we've over here rearranged it a little bit, delta d and our fraction is, once we decompose delta d into this two components, right here, that is our Broyden's method. And again, you might be saying, well, why is there some subtraction up here? Because you see that delta xt of n and that delta xt, but why this is a subtraction and this is just the value at that new point. So why does that not match up? And the reason is pretty simple. And again, this is the part where I'm going to switch to his notation. All right, so quick jump cut. It's 81 degrees in this room right now, which is kind of ridiculous. I'm sweating so bad. I'm so uncomfortable. I've got a massive laceration held together with stitches on my head. So you know what? I'm not going to re-record my entire thing because right after I cut this, I rambled for about 10 minutes and I watched it back and it literally made no sense. I was just like, words were just kind of falling out of my mouth. So I apologize, I don't want you to sit through that. So I'm gonna quickly, again, prove that my interpretation of like Broyden's method right here with my syntax and this structure is exactly equivalent to what Broyden has written in his own notation. Again, my previous explanation that I just cut out was completely incomprehensible, barely human speech. And I think it's because of the heat and the laceration in my brain. So we're just gonna redo that. I'm not redoing this entire derivation. I'm just gonna quickly fix, not fix, but prove that they are the same thing. So directly translating from my notation to Broyden's notation is gonna look like this. J of n is equal to j of n minus 1. We're using k and k plus 1 notation. He uses n and n minus 1, but again, they're exactly the same thing. Plus, we're gonna have f of n, because again, we're using x, k plus 1 notation. He just calls it f of n. I'm going to put the delta t down like he does, because I'm cool like that. he uses double bar, delta x of n squared, and then over here is delta x of n transpose. So this is a direct translation between what I have and what Broyden uses for his notation. So you can see that they're already fairly similar. The only major difference is that I have on the top of my fraction f of n, and he has on the top of his fraction delta f of n minus jn minus 1 times delta x of n. So you might be saying, Ethan, one of those is subtraction and one of those is a set of numbers. How in the world can those be the same? And the reason is actually pretty simple. So what is the actual difference between f of n and delta f of n? Because that notation is a little unclear, I think, personally, and that's why I prefer my own notation. But that's really easy. So delta f of n is simply the difference between f of n and f of n minus 1. So that's all this is. Just like we were doing right here with our delta x, it's the same thing. Even though it doesn't actually say delta x, delta f of n means the difference going to f of n. So now that that's cleared up, if we were to rearrange this to solve for f of n, because we're going to try to go from my notation, to Broyden's, we would see that f of n is equal to delta f of n plus f of n minus 1. So obviously we're just going to move this guy over to this side. Subtracting a negative makes it positive. So this is our substitution. So obviously you can see right here, that's closer. We now have our delta f of n, but there's a plus f of n minus 1. And for some reason, there's a subtraction of the Jacobian over there. So why exactly how do we change this guy out for that? So we're like halfway there. How do we do that last step? Well, the last step's also pretty easy, and it goes all the way back to this linear approximation we made over here. Remember, we've said that some new point on our function can be approximated to be our known point on our function multiplied by our step in our direction delta x multiplied by the Jacobian, whether that be approximate or the real thing. And then because we're looking for the root, we're looking for when f of x equals 0. So we can do the exact same thing, but using Broyden's notation right here. So we'd say that 0, all right, our final point is going to be equal to f of n minus 1 plus our Jacobian jn minus 1 multiplied by x of n minus x of n minus 1. Right here again, that's exactly the same thing we've written down there, but using Broyden's standard notation. And as you can see right here, if we solve for f of n minus 1, f of n minus 1 is going to be equal to the negative Jacobian jn minus 1 multiplied by x of n minus x of n minus 1, which he notates as delta x of n. And as you can see right here, if we were to simply plug this into here and then plug this into there, we'd end up with j of n is equal to j of n minus 1 plus fraction of, well, delta f of n, and then plus fn minus 1. Fn minus 1 is negative jn minus 1 times delta x of n. And then on the bottom is still going to be that double bar delta x of n squared. And then on the outside is still going to be our delta x of n transpose. And as you can see here, since this is just a direct translation of this, I'm just going to write trans for translated. This is our direct translation of my notation and my simplification to Broyden's exact words, using this quick little definition of how he writes his deltas. Because again, we wrote our deltas as just delta x to show it was a movement in the x direction, and he uses it to notate movement in the x direction to a specific point notated by the new point sub n. But again, once you do that little equivalence right there, as you can see, my formula is exactly the same as Broyden's, and so they are definitely equivalent. So thank you. I appreciate your time. I apologize for the jump cut. I know I really like to do one cut, but honestly, I'm real stressed with the temperature of this room and the pain from the cut on my head. So I just want to get it done, and so we're going to go a little sloppy this time. I hope you forgive me. But thank you, and have a good evening.